Okay. Hi, everybody. Thank you for joining us today. My name is Aisha, and I'm one of your Solid State Circuit Society staff members. The topic of today's webinar is Getting Started with Open Source Silicon, presented by Matt Venn. Today's webinar will be a little over an hour, and we'll hold a Q&A session at the middle and at the end of the webinar. Attendees of this webinar have the opportunity to earn a certificate of participation for attending this webinar. I will put a link in the chat box with instructions on how to obtain the certificate. The webinar video and slides will also be posted on the SSCS Resource Center about a week after the webinar. Please use the Q&A section on your dashboard to ask any questions. I now invite SSCS Webinar Committee to introduce our speaker and give a few welcoming remarks.
Thank you very much, Aisha. My name is Boris Merman. I'm actually not on the SSCS Webinar Committee, but Poshwan Wei is, and she's on this call as well. So thank you, Poshwan, for organizing. I am here to provide a very quick introduction because we're dealing with a very special topic today, which is open source chip design and open silicon. And I merely want to highlight here with this slide that you're already seeing that this is a very coordinated effort within the SSCS. We have launched a program in 2021 that features various events aiming to build new communities and democratize chip design. We have the annual Chipathon, we have Coded Chip travel grants. If you want to learn more about this, please go to the website that's listed. And this is all coordinated by a technical committee that I am leading. And our speaker today, Matt Venn, is actually part of this committee, and I'm really excited to have him involved. So a quick introduction on the talk today and the speaker. So Matt Venn is an electronic engineer. He's a science and technology communicator. He's been involved basically from the beginning with open source silicon for about 3 years, has sent 20 chips for manufacture, and has helped over 600 people learn the tools, with 300 then actually taping out. So in my perspective, he's really made game-changing contributions to democratizing and simplifying access to chip design, and we will hear all about that today. Matt wants to keep this a bit dynamic, so please be typing questions constantly during this presentation. We'll try to go through many of them live. I guess Matt has about 4 or 5 places in this talk where he can answer and engage in a discussion. He wants to keep this as lively as possible. So please be prepared for that. And with that, thank you again, Matt, for being available today and for interacting with this community.
Yeah, thank you for the introduction, and honored to be involved and be on the committee. And thanks for inviting me to do this. And just to reiterate, yes, for me, the point of the live webinar is for you to have the opportunity to ask questions. So use the Q&A section of the dashboard to ask any questions as we're going along. And I will also be asking questions specifically during different parts of the presentation. So I'm going to share my screen here. And hopefully, whoops, go up to the first slide. And the slides will also be available at the end of the webinar. I'll give you all a link. So in this talk, I'm going to be telling you a bit about how I got started, because I don't have a ton of experience. Like Boris said, I've only really been involved with ASICs for the last 3 years. This is my first ever chip. I want to tell you about things that I screwed up, that I got wrong. We all make mistakes, and one of the interesting things about the semiconductor industry is it's very secretive. So one of the things that we're doing with open source silicon is learning and failing in the open. And I'm happy to go first and say that I mess up, and it's an opportunity to learn from each other. And also it's an opportunity to do new things, like get ASIC hats. So I've got my ASIC hat here. There you go. If you want one of these, you have to volunteer at one of my workshops. That's the only way to get a yellow ASIC hat. And I'll also be talking about some of the new tools that we've been making and the new ways that we've been getting people to engage with open source silicon, including mixed signal designs. And I'll also be dropping some quotes from some people that I've met along my journey. So, for example, I had an interview recently with Carsten Wolf, the principal IC scientist at Nordic Semi, who's a fellow open source silicon enthusiast. And in his opinion, there's nothing blocking the use of open source tools. It's just a matter of time. We need to grow trust and confidence in the tools. We need to keep on doing tapeouts, and we need to keep on testing the results. So I've got lots of links all in the presentation. And like I said, I'll be sharing the presentation at the end. So if you want to go through the presentation and use it as a resource, then I welcome that. So I had this little placeholder here to ask about you, but I did that while we were warming up. And it seems like we've got a real wide range. We've got people who have done no tape outs, like complete beginners. We've got people who are doing industry. We've got professors and students. And one thing that I've learned through talking to people is that in industry, we have things, it's very specialized. People are siloed. So I often take with me, when I go to a conference, a silicon wafer and a microscope. And even if I'm talking to somebody who's maybe got 10 years in industry, they've probably never actually handled a wafer unless they work in the fab, because they're more used to their specific silo, their specialization. And it's also extremely rare for people in industry to be able to tape out their own designs, because the only people historically who can afford to experiment and play and do fun things are people because the tools have been historically so expensive. So even if you ask people, have you done a tape out? And they say yes, normally it's not the design that they chose to make. So I don't know if you've, the eagle-eyed among you can see in the background, we've got skull and crossbones here. That's actually a design that we taped out, a skull FET inverter. I'll show you a microscope picture of that later on. So just a little bit about me, which is my my second favorite topic to talk about. My first favorite topic is ASICs, obviously, but my second favorite topic is me. I want to tell you a bit about my background. So I'm a science communicator and electronic engineer, and this is a interactive robot exhibit that I built for a science museum in Bristol. And it was connected to solar panels on the roof of the museum and would draw these pictures depending on how much energy was being harvested on the solar panels. I invented a workshop called the Hydrogen Challenge, which has been taken by 50,000 school students so far. I only invented it. I kind of did the first delivery of maybe 5,000 or 6,000 students and then handed it over, and they've done the other 35,000. So I have a big experience in making engaging interactive workshops. And that's one of the things that I bring to the work that I do now with semiconductors. This is the first CE certified product that I made, a split keyboard. So although I'd been doing engineering for a long time, and it's a superpower to be able to bring engineering skills to science communication, because it allows me to build props that nobody else can build or nobody would have the idea to build. But this is the first kind of professional product that I made. And I learned a huge amount on that job, especially the emissions testing, the certification side of things. Digma's a cool company based here locally in Spain, where I live, and they've currently got their next crowdfunding open. So if you fancy a cool split keyboard, check them out. They're called Digma. And like I mentioned before, I want to normalize being bad at things. I think we live in a time where, in the Instagram age, where we want to, appear perfect. People are judging us on social media. It's like you have to be vulnerable to put yourself out there and say you don't know what you're doing. But the internet is amazing for learning and sharing. And it's important to start new things. And when you're new at something, you're bad at it. I wrote this blog post in 2017 about getting started with FPGAs, and you can read it with this link here at the bottom. But it's actually very powerful to be beginner and to be learning, because as soon as you get to be somebody super expert like Boris, you forget all the things that the beginners find hard, unless you're interacting with beginners every day. So you forget how to onboard people. So being a beginner is actually a good place to be. It's great to make mistakes. It's great to share mistakes. And this like list here that I got on the right hand side, I think is kind of my personal way of getting into things. I wrote this 7 years ago, and I still stand by it. I think finding the community and the tools is really important, and then making a project and then presenting the project is very important. And the open source aspect of semiconductors that we have now is really good, is really impacting this. We've never had it easier with semiconductors. Now you don't need to sign an NDA. You can publish what you want. You can study other people's work. And that is just fantastic. I've been eavesdropping on the eFabless Chipalooza design reviews, and I'm learning about analog layout and analog design. And watching all these designs being published and all this information being out there that we can all learn from. So to give a bit of context on the semiconductor specific stuff, which is why we're here today, 2020 is when Google, Tim Ansell, eFabless announced the Sky 130 PDK and the free shuttle opportunity. And that for me was the starting point, really, because although I'd got some FPGA experience and even tried running my early FPGA designs through Tim Edwards' QFlow, which was like an early open source ASIC flow, without the prospect of getting chips made, it wasn't so interesting for me because I'm a very practical learner. But with a free tapeout, I was totally on board. So I got started. I started learning. I was learning in the open. I was publishing as I was going, and I volunteered to do a presentation for Hackaday Remoticon. And in that presentation, I asked who would be interested in a course to learn how to do this stuff. And 200 people said they'd be willing to pay for a course. So that was a really good data point for me. Also, for any entrepreneurs out there, my number one advice is check that you have an audience for your product before you make the product. So I had a ready audience of 200 people, and then I made the course, but I didn't make the course and then try to sell it. Listen to me. I've done 15 startups. Don't waste your time. Find the audience first. Then I did my first tape out, MPW1. So I didn't pay for that. And I put this clock on this chip, and I was very surprised at how much space there was available. So my clock is this one here on the bottom right-hand side. And I dropped it right in the middle, and I had this big area here. So if you're not familiar with the eFabless Caravelle, we get given this pad frame, and then this RISC-V processor and this memory at the bottom, and then this area in the middle, which is 10 square millimeters, which is really a lot. Usually the smallest you can buy is maybe 1 square millimeters from Europractice or XFab, like a traditional multi-project wafer service. And I put my clock in there, and I was like, there's too much waste here. I can't waste all of this on filler cells. I need to get some more people involved. So I invited Richard, Louis, Guillaume, Q3K, Michael, Vamsi, Alexander, all to be involved in this. They all submitted a little design. This thing at the bottom here is a multiplexer. So this was my first fractional tape out. So I had 3 designs on here, and the others were from my friends. So I started the course in February after doing my first tape out. MPW2 followed in June. Chip Ignite is the eFabless commercial version of that free tape out. In October, MPW1 Silicon arrived, and we had problems. I'll go into that in a little bit. more detail. We had another Remoticon, and by this time my course is running and we were getting stuff on MPW2, and this was my second fractional tape out, so I was like determined to use more space. So I got the first 16 people who took the course to do a tape out, and we combined all their designs together onto one die. And I used like a system like this. So everything was connected onto a tri-state bus. And then these highlighted wires enabled those tri-states. So we could enable each project in turn. And this was one of the first open source semiconductor tools that I wrote. So I'm a tool maker. I'm also a co-founder of Yosis HQ, and a lot of us there are also tool makers. And with like, I don't know, there's something really gratifying about making tools and other people using tools. I love it. And this is multi-project tools that I came up with, and has been used in quite a few shuttles to get to use more space on the die. So continuing into 2022, I was able to get my first ASIC to work, even though we had these problems. We had another MPW 5, 6, 7, 8, 9 tape outs that year, all free. So there was no way I could have gotten my start had I not been prepared at the right time, because I probably did, I don't know, $200,000 worth of tape outs, and I didn't have to pay for any of them because the Google funded lottery shuttle was running at that time. We got MPW2 wafers out of Fab, and Tiny Tapeout 1 happened, which I'll talk more about later. And then Global Foundries, another open source PDK, arrived, and there were 2 Global Foundries tapeouts in 2022. 2023, we did Tiny Tapeout 2. We got MPW2 back, and there was no April MPW. So up until that point, there'd been a new MPW, lottery MPW, every quarter. So that was the first sign that maybe that was going to end. MPW6, we got a hot lot received in May. That was to try to fix the issues that were found in MPW 1, 2, 3, 4, and 5. And that at that point, everything started working as expected. We did Tiny Tapeout 4 in July, and we did a live public silicon bring up in October, which was crazy. Like I said, one of the nice things about doing open source stuff and learning in the open is doing new things that people haven't done before. So normally companies are very secretive. Nobody says they failed their tape out. They want you to think they get it perfect every time. It's not true. Ask anyone in industry. And we decided to do a live silicon bring up in public as a kind of world's first. And luckily, things worked out. It was pretty stressful. I didn't enjoy it that much. But it felt like a good thing to do that in public, especially because we had involved so many people in it. We had GFMPW1 tape out in December. And there's a few more things that have happened in 2024, but this is kind of to bring you up to date with the context of the open source silicon community. And it's a growing community. There's 6,500 Slack members on the open source silicon Slack. Click this link to join. The OpenLane GitHub, which is the open source ASIC flow that I most often use, has got 1,000 stars. OpenLane 2 is in development. The Skywater PDK, the world's first manufacturable PDK. There's 1,000 public projects submitted on the eFabless website for the Google-funded MPW shuttles. And interesting that we've got more PDKs coming. So the IHP 130 nanometer BiCMOS is a very interesting PDK, very interesting for research in analog, supports up to 300 gigahertz. Now, I don't know whether we'd get there with the open source tools, but it's quite an amazing process. And then at the other end of the spectrum, Pragmatic makes a flexible semiconductor process. It's only NMOS. It's only a few metal layers. It's pretty limited, but they can do like a chip turnaround in about 2 weeks to 1 month. So there's some interesting things to happen there. So a little bit of info on what happened with the MPW1 silicon. There was an issue with the clock tree, and so hold time violations happened because we had too much skew on the clock tree. I wrote a blog post about it and posted a video. The fix for the tooling came in MPW3, but all the issues weren't flushed out of the Caravelle harness until MPW6. That was that hot lot. So from MPW6 onwards, things got easy. But for MPW1 to 5, the silicon needed a lot of fettling to get working, which was a real shame because those early designs were very difficult to make measurements from. And I did get my stuff to work, but only by very, very careful control of the supply voltage and twiddling with the GPIO configuration. And just to highlight another thing that was an issue, a problem that I had, my first demo designs made a frequency counter, which totally failed, and I never got to the bottom of why it failed. This was the way I instantiated it for the first shuttles. Clock reset signal segments digit period low period. No debug, no insight into the design whatsoever. So if anything went wrong, no understanding of what could go wrong. And then this is how I do it now. So we have a debug selector, and I can turn on and off access into the design and get visibility inside. I can read out the debug state. I can read out the clock counters. I can read out the edge counters, all from inside the design. So as you learn, as you do these things, you learn, and it's cheaper and easier to learn now than ever before. Now that the cost and the barriers to accessibility is much lower. So again, going back to making mistakes and learning from your mistakes, the semiconductor industry has traditionally been extremely conservative because of the secrecy, the huge investment costs in IP, the big costs of making mistakes and errors. And all of these things now enable us, using the open source tools in the open source community, to learn much faster. And that gives us a pretty cool edge, in my opinion. So before I get on to the next part of the presentation, I'm going to show you some tools, give you an overview of the tools. Here's the skull fet again in the background. I want to pause here and ask for any questions. Does anyone have any questions for me? And how do I find the questions?
There is a Q&A menu, but there's currently no questions in there.
Okay. I've seen one comment from Sergio saying, can you provide more details on the clock issues in the eFabless harness? I would say when I share the link to my presentation, you can read more about it on this blog post here. Lewis says, if the shuttles are over, what is the cost of fabrication? So there's two ways of doing this. I'll talk a bit more about fabrication later. The open source lottery shuttles might not be fully over. The Google sponsorship has ended, but somebody else could step in. They weren't the only people that were asked in the beginning. Maybe someone else will step up and do this, and we'll have more of the sponsored lottery shuttles. eFabless runs a lot of competitions. They had the AI competition. They've got a machine learning competition coming up. There's Chipalooza. And if you apply for any of these competitions and you get in, that usually means your design gets fabricated. So definitely follow eFabless and watch out for their competitions. If you're in industry, you can pay $10,000. You get 100 QFN chips from eFabless, and you get 10 square millimeters. So that's very good value for money, because if you compare that to, say, Europractice, 1 square millimeter will typically cost you $5,000 for 50 samples, and they won't be packaged. With eFabless, it's $10,000, but you get 10 square millimeters. So you get 10 times the space. You get double the number of chips, and they're packaged. So definitely check them out if you've got the budget or you need a closed source design. The cheapest way of doing a tape out now is with Tiny Tapeout, and I'll talk more about that later on. What are the PhD opportunities in this field? Boris, maybe that's one for you. You want to mention anything about that?
Yeah, I think you find various groups now, including my own, actually interested in building up flows and particularly develop new EDA tools, right? So now that it becomes much easier to deal with licenses and this whole connection to the Python world with these open source tools, I think there's a whole slew of new development opportunities for EDA, design automation, automating analog sizing, automating analog layout. So many people are working on that. So I think there are tons of PhD opportunities in that area.
Thanks, Boris. I'd say, yeah, also if you're on LinkedIn, that's a good place. That's where a lot of the discussion happens. Follow the ASIC hashtag, follow the semiconductor hashtag. Follow me on LinkedIn. I'll give you a link at the end of the video. Whenever I see these opportunities, I repost them.
Yeah. So Matt, there is one more question in the Q&A. What have you learned when implementing the analog flow for Tiny Tapeout?
Oh, great question. Maybe I'll come back to that because I've got a whole section on Tiny Tapeout.
Okay.
Kostas says, what is the cost of packaging and testing? Kostas, actually, it's rare to get bare dies. You're much more likely to get QFNs, which are easier to solder and handle. And at least with the eFabless service, they also solder them onto a little breakout board so that you can get started. With Tiny Tapeout, we also solder them onto a breakout board. Here's one here. Probably my screen is quite small, but I'll show you some pictures later on in the slides. If you want bare dies, that's usually more difficult, and then you do also need the more expensive equipment, or you need a wafer prober, or you need to do wire bonding. And then yeah, I see the Q&A section now. Alan says, I'm a complete newbie. Overview of terminologies, any websites, presentation, or any write-ups would be useful to refer, if possible, to share some pointers. Sure thing. So if you go on my course, I have a terminology page that lists all the 3-letter acronyms we use. And also, if you check this, I've done a few of these, like Remoticon 2021 and Remoticon in 2020. They're like hour-long YouTube presentations for these conferences. You can watch those conferences, and that should fill in a lot of details. The whole idea behind my 0 to ASIC course is going from 0 and assuming almost nothing. I do assume a bit of Linux and Git experience, but I don't assume any semiconductor experience. So check out the course, check out my YouTube channel. There's a lot of information there. Cool. Okay, so let's continue then.
So there are a couple more in the Q&A, but we could take them later. One says, what are difficulties you faced while implementing analog chips in the open lane flow? And what makes an engineering workshop successful? That's a big one.
That's a great one. Yeah. Yeah, I'll come back to the analog one. Boris, you can help me not forget it.
Yeah. We'll keep track.
What makes a successful engineering workshop? Great question. I think going into the workshop with an open mind and being prepared to learn from it. So have a plan, but be prepared to change that plan and write down everything that you're learning. Try to get some volunteers to help you so that you have some space to kind of withdraw from the workshop and watch what's happening. How's it going? And always have a questionnaire at the end that is full of questions that will help you improve it. Did you enjoy it? Did you learn? What did you enjoy? What didn't you like? What could be better? And make people fill that out. Build the questionnaire into the workshop So don't let people leave without filling it in. Every time you run a workshop, you want to get like another 10 or 15 responses like that. That gives you the feedback. That's how we learn, with the feedback. So set yourself up to win by getting a good learning feedback cycle. So that's like very general. I would advise anyone doing that with any workshop. For engineering, and probably other things as well, I think it's important to address people's different ways of learning. Like some people really want things to be practical, some people want theoretical, some people will go slower than you expect, some people will go faster than you expect. So you want to be prepared to handle these cases. So if you get someone that's bored and they want to go faster, you have some like extra higher level stuff. Sometimes also you can get people to like move from the volunteer position and into an assistant position. And if people are really struggling, then have some very clear, easy goals that people can get through and then feel good about getting through. Yeah. With engineering as well, and especially with engineering, we're almost always using computers. And when you're using computers, things always go wrong. So you want to be prepared for things going wrong with computers, internet connection not going right, tools not downloading, problems with serial connections to development boards. You want that stuff prepared and out of the way early. Bring a spare computer, bring spare setups. Having people work in pairs is a good way of dealing with that. And that's also a good way of sharing resources. Like if you've got expensive resources, you can get people to do things in pairs. That can often also just make the workshop better because people enjoy working in little groups. So thanks for that question. I enjoyed answering it. And I will keep going now. So and here's the I promised you the micrograph of our skull-fet tape-out. One of the fun things that you can do when your boss isn't breathing down your neck about not messing up the next tape-out. So we made a MOSFET in the shape of a skull and then used two of them to make a skull-fet inverter, which worked. And this was taped out on quite a few different shuttles, done by my friend and colleague Uri Shaked. So here's another quote from a mentor of mine, an anonymous engineer at one of the world's largest chip design firms. You're almost certainly, half of you are probably using hardware designed by them. And he's also very involved in teaching as well. And he thinks that the open source tools are fantastic for learning. So for any newbies out there, for any professors, for college, for even for industry, if you've got, you're paying a lot of money for these expensive tool seats, they're always in contention. How do you do the training? You can learn all the same stuff. You can learn how to do STA. You can learn how to do verification. You can learn how to write formal verification assertions with the open source tools. So you can get much more applied, much more practical training by using the open source tools, even in industry, but especially for academia. Having things easy to install, easy to maintain, or accessible on the cloud makes it easier for self-study, makes it more accessible for VLSI to a larger population of students. And we've seen this. We've done tapeouts with countries where they're doing their first tapeout as a group of students in a country because they never got the expensive tools because their university wasn't prestigious enough. So awesome open source ASIC resources. If you click on this link, you'll go to a GitHub repo with like hundreds of links to it. Here's some digital focused ones. OpenLane, I've already mentioned. Open Road was like arguably a huge and very important part of the world of open source silicon way back before I was involved. Boris did say I was there from the beginning, but it's not really true. It was true for the second wave of open source silicon enthusiasts. But Open Road was DARPA funded. And the idea was to make it like a hands-off HDL to GDS flow. And it provides a lot of the core of what's used now in OpenLane and some of the other open source HDL to silicon tools. Coriolis 2 is another one, a European one. OSS CAD Suite is a collection of a bunch of different tools, and that's maintained by Yosis HQ, another company that I'm involved with. I'm a co-founder of Yosis HQ. And there's also things like System Verilog support and VHDL support with plugins for Yosis. On the analog front, Magic, very old school layout drawing program, 40 years old, created by the author of Tickle as well, now maintained by Tim Edwards. And that's used to be, you had to used to pay to get a floppy disk. But I think it's always been on a permissive license. So that's like open source ASIC tools going back 40 years. K-Layout is like a modern version of Magic. Got the same key bindings as Cadence. So it's liked by a lot of people who have industry experience. NetGen for LVS, Xscheme is what we're using for schematic capture. ngSpice for simulation, Zeiss also for simulation. Zeiss is another DARPA-funded project. GDS Factory is a Python library, originally for photonics, but people are also using it for automated layout. And OpenEMS is a full-wave solver. So we have a lot of stuff that's there ready for us, but there's still a lot of stuff missing. In particular, there's a lot of stuff on the RF IC design tools, and also tools that is like more important on the more modern process. So the only PDKs I've taped out on are Sky 130 and GF 180. And as you go down, as you get smaller and smaller, or you move to FinFET, you often need more or better tools that we don't really have access to yet. Important types of analysis for analog. Transient noise. I'm not an analog expert. I'm not an expert at all, to be honest. So these are things that I've been told by experts. If you're not an expert, then get some mentors, get some friends who are experts. That's my advice. Lacking on power simulation and gating, and like clock distribution and gating. And also missing some proven analog IP, but there is a lot of recent progress in that area. And we've also seen a better mixed signal co-simulation. ngSpice 42, that's the latest one, now works with Verilator. So you can co-simulate with a Verilog design that will then drive your analog SPICE netlist. And I've checked that works. Doesn't work well. We've just tried it with an HDL called Amaranth, and it falls over a bit there, but that's like a Verilator Amaranth thing, less ngSpice co-simulation thing. It's definitely worth checking out if you're doing mixed signal. And here's another quote from Jörn, who's an independent ASIC engineer. Might be like a beginning of a new breed. Normally, you wouldn't be a professional independent ASIC engineer because you would be working inside a big company accessing their expensive tools. But he is now doing professional closed source tapeouts with the open source tools. And he's working remotely. He's working while he's on his skiing holidays. He's working in small teams. He's someone you can follow on LinkedIn if you want to find out more about professionals using the open source ASIC tools. One of the other amazing things about the licensing on the open source tools is being able to run them in the cloud, run them in Google Colab or Jupyter notebooks, running the whole flow, being able to do everything online. That's incredible for training because you don't need to download the tools. You can do the simulations, you can do the layouts in the web browser. Whoops. And this is an interesting bit of work that I did a collaboration with a guy who now is working for NVIDIA, Teo, used to be at Oklahoma State with James Stein. And he did some work on optimizing adders. So with the open source tools, when you made an adder, it always just used something, a topology that's kind of in the middle of the power performance area matrix. and he implemented a Yoast plugin that allows you to choose the topology to make a faster adder. He instrumented a RISC-V processor booting Linux and found that 60 to 70% of instructions use addition. So if you can get a faster adder in the ALU of your processor, everything's going to go faster. And we taped out 5 different topologies on MPW6, and I have a paper in process. And this is the silicon results. Maybe it's illegal for me to share my silicon results, but here we are. Pretend you haven't seen this. And you can see that the behavioral, the ripple counter starts off extremely fast for very low bit widths, but quickly gets slower and slower. Up here on the left-hand side is the delay between getting the result from the input. And then we get much better results from the Brent-Kung or the Sklansky topologies. And also, I've been developing my own open source tools. So this one is called SillyWhiz. Sing it with me. Everyone say SillyWhiz, which is a open source in the browser analog layout and simulation tool. Because the first time when I started doing analog, I couldn't believe how long it took. It took me like a day to draw an inverter and then simulate it. So I was like, I'm going to fix this. I'm going to work with Uri, and we're going to build this in the browser. So here's an NMOS. Here's the stack up on the right-hand side here. Can people see my browser window here? You can see SillyWhiz. Great, thank you. So on the right-hand side is the cross-section. On the left-hand side is what you'd be drawing. And then we can flip it straight into simulation mode. So if I delete this gate and draw a new one, a thinner one, you can see I get more current flowing as the MOSFET turns on. Blue is input voltage on the gate, and orange is current flowing between the source and the drain. And it's literally that easy to experiment and play in the browser. So we've got a very simplified PDK. Shout out to Tim Edwards from eFabless, head of analog, for helping me put together this simple PDK. Shout out to Holger, a maintainer of ngSpice, who helped make a 2 megabyte version of ngSpice that we compiled to WebAssembly that runs in the browser. That's why it works. Look at this interactivity. It's just incredible to have, like, to be able to do this, play with it in the browser. You can even download the STL if you want to do like a 3D render of your cell. Here's an inverter, PMOS, or if I load the NMOS, this is like, back in the day, you use a resistor for the pull up on your inverter, this yellow block here. And problem with that is that when the MOSFET is on, you're wasting this current, this green current comes up. So that's why we switched to CMOS. So we put an NMOS and a PMOS together, push pull, and now we get a much faster turn on and less current being drawn. So you can teach all of this in the browser. Load the SkullFet, somebody says. There you go. Working SkullFet. Yeah. If I delete it, the simulation breaks. So this is an amazing tool for teaching this important stuff in the browser with no tool download. And if you want to get started with your students, we have lessons here. Resistor, parasitics, voltage dividers, going all the way to CMOS inverters, covering the whole thing. Then when you taught that, then you move on to using inverters to build digital logic, which I'll get onto in a bit. So I'll pause here for another round of questions. Well,
Yeah, we have quite a bit of stuff here. start with something basic here. Do you have internships or volunteer opportunities for undergraduate students?
Yes. Just get in touch with me on LinkedIn. Don't connect with me on LinkedIn with no message, otherwise I ignore it. Connect with me on LinkedIn and say, I saw your IEEE webinar and I want to be an intern, so I know who you are.
Okay. Another question is, where are the open source tools placed at the moment for lower technology nodes?
As in lower, as in smaller?
Yeah, I guess so.
Yeah, so Open Road has been used down to 20 nanometers, I've heard, but I don't know much about it because as soon as you're using a closed source PDK, you have to sign an NDA, and that means a lot of that information remains private. So I know from talking and interviewing the various Open Road team, like Matt Liberty, check my YouTube channel for some interviews with the Open Road team, that they have done successful tapeouts down to 20 nanometer and FinFET, but I don't know anything about it. So you'd have to get in touch with them.
All right. So do people do Sky 130 for PhD research?
Yeah. I think a lot of people do that. We're seeing more and more papers being published that reference the Sky 130 PDK and the open source tools. And when I poll the people who apply to Tiny Tapeout, we see the split is about 50% academic, 50% amateur. So hundreds of people are doing academic tapeouts using Tiny Tapeout, and that's based on Sky 130.
Yeah. Let's see. I still get confused between tools, workflows, and entities. Is this clarified on your website? Or there are a few questions about, where can I find the tools? Are there lists on the web? Maybe you have some special pointers for these people.
Yeah, I would go here. Awesome open source ASIC resources. There's a lot of stuff here, and actually, Andreas Olofsson, who's leading the company behind Silicon Compiler, I think his one is probably even better now. So you could check that one out. Yeah. Next question.
Yeah, I think I'm not sure I understand the question. Are we into VHDL already in 0 to ASIC course? I don't know.
Yeah, I mostly focus on Verilog. I don't mind what HDL people use, but Verilog is the best supported for the open source tools. But there are plugins for VHDL and plugins for System Verilog that both work pretty well and have quite good coverage. But I'm not really an expert in either. So I'm happy to give pointers, but I couldn't even do my own VHDL design, to be honest.
Yeah. What are the limitations of open source tools you shared in terms of process nodes or number of transistors, etc.?
I would say probably 10 million transistors, order of magnitude. There's a lot of development. So one of the big bottlenecks there is, there's maybe like 10 or 12 tools in the whole ASIC flow. One of the bottlenecks is Yosis, maintained by Yosis HQ, but we are doing a lot of development work on that at the moment. And we've got some fair amount of investment coming in to improve the ASIC performance on there. So yeah, and if you compare it to like PPA figures for the proprietary tools, which is very difficult to do because they don't allow that. But kind of word of mouth and things that I've seen or heard, I would say that it's kind of maybe roughly half, like better than half is good. So you might get like twice the area or like twice the like half the efficiency. It's like improving, but yes, lagging behind. Can't really compete with an industry that invests tens of billions of dollars every year. Personally, I don't see that as an issue, because I think one of the most important applications for these tools is learning, and PPA is less important for that. Or it is, and you're like really focused on something, you're writing a paper about it, and then you're actively like working at the bleeding edge, and having access to the tools allows you to improve them. So like Teo was able to compare his PPA figures for the adders and was able to surpass the figures you got from industry on this one specific area. So you can still like do this stuff for research, for academia, for doing cutting edge stuff.
All right, so I don't know, you want to move on?
Yeah, I think I'll move on, because I'm actually going, I didn't think that, I find it hard to talk for an hour, but I'm finding it fairly easy now. Nearly up to the top of the hour.
It's
We've
a
got
good problem to have, yeah.
90 minutes, isn't it?
Yes.
Okay, and we're doing Q&A as we go. Yeah. Okay, so example projects. Here just some of my favorites. This one is a microcoded USB device, so pretty useful. You can load in what the endpoints are, and then the design takes care of all the hard precision timing stuff. So you can drop this into your design and then build a fairly configurable USB device. This is a PLL for a 5 gigahertz amateur satellite transceiver by Thomas Parry. And here's another quote from Thomas Parry, who, since I first met him and interviewed him, has started a company called Spherical Systems using the open source tools. And they've done their seed fund. They've got they're employing people. They're based in the Netherlands. If you're in the Netherlands and you want an open source silicon job, contact Thomas. He's always looking for good people to hire. And yeah, he's definitely progressing as a CEO. Look at his kind of industry speak language here. Delivering value, operate capital more efficiently. So check out Spherical Systems. Fuse Risk, really interesting. This is using the fabulous FPGA fabric, where you can basically make a Yosis compatible FPGA fabric, and it's been instantiated between 2 RISC-V processors. I think we're going to see a lot of stuff like this. You know, you buy, if you're in industry, you make you buy an off-the-shelf chip, you use it, but probably you're only using like 20% of its peripherals. A lot of that silicon remains dark, but you still had to pay for the silicon. So there's a good niche here. If it becomes easier and easier to do SoCs with a bit of FPGA, a couple of RISC-Vs, a bit of mixed signal, just for your application, you know, Nordic Semi only moved away from 130 nanometers a few years ago. There's still a good niche here for doing industry compatible stuff, especially with mixed signal. Subservient, that's Olof Kindgren's award-winning 1-bit serial RISC-V processor. Analog neural networks, there's a lot of interest in analog neural networks as an alternative architecture for the digital one. RISC-V with a 5 gigahertz transceiver, 8-bit SAR A to Ds, RISC-V Arduino compatible design. All of these links go to the projects, by the way. Delta Sigma Audio DAC, Microwatt, project from IBM, OpenFASOC, project from METD, who's also on the committee, and the latest Pico challenge. We're going to be using his latest tools. So if you're interested in automated analog layout, make sure you follow me or Boris or any other the people on the committee on LinkedIn to get involved in that competition. And from Harold Prettel, who's one of the people involved in this Delta Sigma audio DAC. He's a professor at JKU, 20 years in industry, worked for Nokia, did a lot of mixed signal radio stuff. Again, open source tools are a great way to get into industry. You can show your work. You're not burdened by NDAs. You can do a tape out. You can bring your chip to the interview. Pretty compelling. Okay, next section is tiny tape out. So let's just pause a little bit for any questions on this last bit on the example projects.
Not so specific to that. There's more questions on tools. Maybe we'll just take one here. Are there tools where we can simulate an FPGA like Walkwi, where we can simulate an Arduino?
Well, yeah, Walkwi is a fantastic tool for simulating an Arduino. And if you're running an engineering or a STEM workshop, Walkwi lets you build in the browser your designs, and you can add things like LCDs, and you can add an Arduino or a breadboard, and you can connect this up, and you can do it without needing any hardware, which is a great way of getting started. For an FPGA, you can do a lot with simulation. You can start your digital design journey in Walkwi in the browser, and then you can move to Verilog. There's a good online Verilog tool that doesn't need any downloads, and then you can move to the open source FPGA tools to design, simulate, verify, formally verify, and create bit streams for. You don't need an FPGA right up to the end. You can learn a hell of a lot without buying any hardware. So I know that hardware is one of the things that is a barrier to entry because it costs money. But you can learn a huge amount. I was just asked today on LinkedIn, can I get started with no hardware? And the answer is definitely a resounding yes. Okay, so let's move on then to tiny tape out. We're on a time budget here, people. No time to waste. What slide am I on here? 39. Okay, we're doing all right. So tiny tape out, lowering the barrier to silicon for makers, schools, universities, hackerspaces, entry-level digital design courses at universities, open source silicon enthusiasts. Give me an emoji. Give me a thumbs up if you're an open source silicon enthusiast in the chat. Yeah. Mike McGivern, good to see you here. Thanks for attending. The Logic Destroyer, of course. Yes. Good. Welcome to the club. Inclusive club for anyone that wants to join. About our community. So, yes, we've got like students and teachers on the one side, hobbyists, hackers and makers. We've got people from industry. At the moment, Tiny Tapeout only supports open source design. So a lot of industry people are a little bit hand-wringing about open source. But I feel like if you're in industry using the open source tools, then you can go to eFabless and pay 10 grand for a private tapeout. It's not 10 grand's not that much money if you're in industry. We build and test in the open. I've interviewed Sylvain Minot, who's done a lot of work on the multiplexer. Jeremy helped with the STA. We have a public Discord chat server. We build our designs. Everything is published online. We had a community call. It started off with a very slow scan chain. Again, I came up with I checked the audience. There was demand. I made a very simple design, Tiny Tapeout 1 and 2 and 3 all used a really brain dead scan chain, which worked, but was very slow. And then once the audience was there, we improved it. We had a community meeting with 15 people. We decided on a fast multiplexer version. The winning design got implemented by Sylvain Minot. And that's what we're using at the moment. We did like a design review. We've done a verification review. We're using OpenLane 2 now. We did the world's first live stream silicon bring up. Everything is done in the open, and this is like part of the giving back to the community and showing how this can all be done in the open. So how do you get started with doing a tape out with Tiny Tapeout? Here's a really simple design. The stuff on the left and the right is kind of outside of the ASIC, and the stuff in the middle of the box is what you put in the ASIC. So here's a walkway project. So this is the design mode where you can like add the elements. So you can go to add down at the bottom in the logic section. Here's our standard cells. Add a NAND gate, for example. Then we move into simulation mode. And here I've got 3 inverters going into some AND gates. I want to get this last LED to come on, so I can come over here. I can start playing around with these switches, try to get that last LED on, and when I get it set correctly, the LED comes on and I'm ready to go. That's my design. Fine, I'm happy with it. Then we use the open source tools all running in a GitHub action to build the GDS files for doing a tape out. So here's that puzzle box. Just set the puzzles correctly. In my info.yaml, I set this number to be the same as this number here, so it knows where to fetch the design from. It gets exported into a Verilog netlist. When I submit this, it automatically runs a GitHub action. One of them is a GDS action. And then I get my routing stats, the utilization, the wire length. I can see what standard cells are in use. So even though I used these standard cells, it's been synthesized down to just one gate, NOR 4B. I can click on that. It's open source. I can see the standard cell layout. I can see how it's put together here. I can see the 2D viewer, a lot of space, about enough for about 1,000 standard cells. I can open the 3D viewer. So along the top, we've got the connections for all the I/O pins. And over here, we've got the cells in use. On the right, we've got the stats. So there's my NOR being highlighted there. I can hide the fill cells so you can see how empty it is. I can hide the wiring. What's this one here? That's the NOR. And I can isolate this. And then on the right-hand side, I've got my layers, so I can like turn off metal 1, or the connections, or the local interconnect. And now if you've done the SiliWiz, you know how these polysilicon running over your diffusion works as transistors. You see the CMOS here. This is giving you the whole end-to-end understanding of how semiconductors work. So then you have the GDS, and that can then be used as part of the Tiny Tapeout project. This GDS logic block gets plopped into the rest of our design. You can also use a hardware description language. So here we have one of the designs I use for the 0 to ASIC course. Instead of giving that number of the walkway design, I give it a list of my Verilog files. And here I'm telling you what the inputs and the outputs are. If you want to learn more, you can look at this. You can check the source here. I've also got a test bench. When I commit, the GitHub action runs, GDS runs again. I've got more cells here. I can learn more about how my design works. 40% utilization. See much more stuff going on. I can again use the 3D viewer. Still got room for more stuff down here at the bottom, all these tap cells, if I hide them. Filler cells. And I've got my 24 IOs and my clock and reset up here for use however I want in my design. So this is amazing if you're running at a community college, if you're doing a drop-in workshop. No one has to download any tools. You do it all in the web browser. No one has to sign an NDA. You can teach the entire stack in the browser with like very little preparation. This has really never been possible to do, and this is all possible with the open source tools. Boris said at the beginning, I'm one of the people responsible for democratizing silicon, but I just want to remind you all, this kind of work is only possible because of all the other people being involved, all the other work that's happening. I'm really just standing on other people's shoulders and making this applicable for learning and science communication. So don't forget to give a thumbs up for all the people involved doing all the other open source tools that all of this is built on. So for example, we ran a 3-hour workshop for Hackaday SuperCon, and we got 30 people to do a tape out in 3 hours. Can you imagine? So we, admittedly, most of them only taped out like a single gate, like an AND gate or an OR gate, but we covered the entire stack. They did a tape out at the end. They had their one AND gate or their OR gate, and then they had a few days left to add and complicate to their design if they were inspired to before the tape out, before their design was locked into silicon. And we just did that again for Hackaday SuperCon, for the Europe BerlinCon, where I met Logic Destroyer face to face. That was great, and other people from the community. And we did a workshop with 20 people, and we got them to do a tape out in just 2.5 hours. It was a bit more of a rush. 2.5 hours was really too short. But then they had a whole week to build on their design before the tape out. So this is totally doable now, stuff that was impossible just a few years ago. So some project picks. What can you do if you have more time? With WalkWe, we see people doing binary to digital converters, LFSRs, population counts, RGB LED drivers. For HDLs, there's really no limit. We see CPUs, Cortex, RISC-V, FPGA. Hirosh has just taped out a Linux-capable RISC-V CPU. It took like the biggest chunk of tiles on Tiny Tapeout, but he did it. And we also have enabled analog now on Tiny Tapeout 6. So this is a 555 timer rendered in gold and black, which I love. Look out, shout out to Maximo Balestrini for doing such awesome renders. I use his artwork all the way through my presentations. And this is what Vincent Fusco said, the author of that 555 designer. He's a professional analog IC designer, and he's mad he has to go to work tomorrow to use the commercial tools. He's amazed he can do an analog tape out for less than $1,000 now. So Tiny Tapeout stats. We've done 5 so far. 6 is closing tonight. We have hundreds of people involved, and we're shipping designs, shipping chips. People do leave it to the last minute. Green is Tiny Tapeout 6. You see this big surge here. And Tiny Tapeout 6 is doing our best so far. Let's just go to the homepage. 3 hours left. If you want to get involved, it's not too late. There's still 6% of the area left. 100% of the cheap PCB sold, 93% of the analog slots used. The green ones are the analog projects. So it's still got a little bit of space up here. Really good utilization. 93% of the area used. And look how much progress I've made in 3 years. That first design with all that empty space. Now we're really getting a lot better utilization, getting so many people on these shuttles now. But don't leave it to the last minute. It's way more work for us in the support forums, helping you all out on these last 2 days when we had like another 40 or 50 people to the project. Get involved earlier, please, for my mental health. And we make everybody submit a little bit of documentation, because when we ship your chips, you get your design, but you also get those 500 other designs on there. So you and everyone else can learn and play with these other designs. One of my favorite artifacts of this project is the data sheet. So you can like look at the data sheet online. If we go to the website, Tiny Tapeout Chips, you can choose one of these previous ones. Here's the shuttle map. You can choose one of these designs and then you can read how it works. You can read how to test it. Well, you could if they were told you how to test it. So please fill in the documentation so people can test your design for you. And this is like such a fantastic resource, such a great thing to have a data sheet with all the designs on it, and really good for academia as well. So you can have your students submit designs and then the next year's students do a bring up of those designs and document what went well, what went wrong, learn how to do better tapeouts. We should make it so that every student does a tapeout before they finish their undergraduate. Why wait for a PhD? Do a tapeout while you're an undergraduate. So we have quite a big verification effort, all using the open source tools. A big part of that was a community review, and I'd especially like to say thanks to Mitch Bailey and Mike Thompson for their expertise on this. We have continuous integration running verification at the gate level, as well as RTL plus formal verification, thanks to Yosis HQ. And we did this live Silicon bring up. Luckily, it works. And we got Silicon results on a live stream. Hooray, it worked. One of the designs we tested printed this message out on the LCD. If you want to watch the live stream, you can check it here. And our customers on Tiny Tapeout are getting their boards back. We've sent about 300 boards out so far for Tiny Tapeout 2 and 3. This is an example project. And here's another one. I won't spoil what is on this best chip in the world. It's a great video by BitLooney. If you're interested and it's pretty fun, go and check the YouTube link out later. So this is what we're shipping now for Tiny Tapeout 4, 5, and 6. You've got your ASIC here. It's mounted on a board if you want to build your own demonstration board. Everything is open source hardware. It's all documented. You can get the specs here. We're using the RP2040 as a coprocessor, so you can plug that into your computer, and then with the Commander web application, you can connect to it, enable any design, look at the documentation, give it any clock speed you want, give it the different interface, toggle the IOs, write Python programs to give it stimulus and measure the response. And we're working on connecting these up on the internet. So we'll have all the Tiny Tapeout chips available online. So even if you don't have a copy of a chip, you could still test somebody else's chip. And this is something that I'm actively looking into, also how we can do this for analog. Analog designs are harder to test. I'm hoping to get some sponsorship for some expensive test equipment so we can have this test equipment online and you can log in and you can use it with one of the analog designs. So all of this stuff is free. The Tapeout isn't free, but we do have sponsorship from eFabulous, so it's very cheap. The early bird price, the first 100 ASICs are your design, the area, the ASIC, the PCB, all for $150 plus shipping. If you miss the early bird price, it's the first 100 are that price, and then we have more available for 300 plus shipping. Still very good price. And this is only for your first design and only for individuals. So if you're a university or your industry, you've got to pay the $300 price from the get-go anyway. You can just buy a single tile. You don't even need the ASIC. So you could submit area. We separate the area from the design. And the reason for doing that is for in a school, you could have like 10 people submit a design, get a PCB back, and then you're only paying $700 for those 10 people to put designs on and get an ASIC back. So very compelling for getting stuff down for real silicon. But as I said, you can do the simulation, you can do the verification, you can use the GitHub resources. All of that is free. It's just for the last part. If you actually want your design on silicon or you want the chip delivered in your hands, you've got to pay. If you want to know how chips get made, I had an incredible chip to the IHP semiconductor factory. Watch the video here. Really I thought this video was going to do way better than it did. It only had like 7,000 or 8,000 views, but I've never seen better footage from inside a fab. Really got unprecedented footage. And I also put a lot of effort into the animations in explaining how all the processes work in chip manufacture. So if you want to learn how things actually get made once you send off your GDS, check this video. And finally, one of the great other opportunities that I had was taking my open source chip to a synchrotron and getting it X-rayed so we could compare the 3D structure of the chip to the GDS. And again, this was like one of the things that came from the open source tools. These guys were doing this stuff, developing this equipment to X-ray chips, but they were using chips that you could buy off the shelf. And of course, you can't get the GDS of those chips. So they were super interested in getting my chips because I could provide them the GDS, and then they could get the results from their tools and then compare to the GDS and see how well their 3D X-rays matched to the PDK and the GDS that we submitted. So if you want to see the results of that or the video, check this link. So that's the end of my presentation. I promised you the link to the slides, bit.ly/SSCS-webinar, scan the QR code, sign up to the newsletter, subscribe and like my YouTube channel, connect with me on LinkedIn. Here's my socials. And if you want to learn everything about it, then take my in-depth course. I've got an analog course in development that will soon be available if you want to learn analog and mixed signal. And we'll spend the last 10 minutes on Q&A. So thanks everyone for watching and being involved. And thanks Boris and IEEE community for inviting me to this webinar.
Thanks so much, Matt. Can we do a couple more questions?
Yeah, my voice is still lasting.
Okay. So I want to get to the ones that have been pending for a while on difficulties you faced when implementing analog in the open lane flow, and what have you learned when implementing analog in Tiny Tapeout? Your perspective on that is asked for.
Yeah. Good question. Yeah, analog is quite different. It's the open lane flow is very like set and forget. Works for a lot of designs. It's works just very easily. You put your Verilog in, you get the GDS out. For analog, it's way more hands-on. There's a lot more you have to know. I don't even really know circuit design, so I found circuits on the internet and then I used them for layout. So there's like just forgetting the circuit design and just imagine you already had a circuit, you just needed to tape it out. There's kind of a bit less agreement about which tools you should use. We've got like the K layout and the magic camp. Well, let's actually start with schematic capture. There's Xscheme, that's the main one, but there's also Quux, and some people even use KiCad, or you could write just Spice directly if you wanted to. But the first part is analog capture. Then there's simulation, ngSpice. Xscheme and ngSpice work pretty well together. And you can see my, I've got like a couple of demo designs here. Like this is a mixed signal one, very simple mixed signal design. Little analog, digital block here, and then like a R2R DAC here. You can download this, and then in the Xscheme directory, you could load the test bench and run the simulations. Then once you've got your simulations ready, you export the Spice. You can then use Magic to generate all the P cells, so all your cells match, or you can create them yourself. I like to use the automatic version. If you're using K layout, then you can import all those standard cells. If you're using Magic, they're already there for you. And then you've got to do the wiring. Then you've got to do post layout, simulation, and LVS. And it's all very, it's much more laborious and kind of manual. I would really recommend Harold Prettel's OSIC tools. IIC OSIC tools. This is a docket. It's fairly huge. You need quite a lot of disk space for it, but it's got all the PDKs installed, all the tools ready to go, and then a whole bunch of shell scripts that let you do things like running DRC and LVS. That it's all been written by like pros who know what they're doing. And then yeah, I've got my analog course on the way. Analog wait list. So if you're interested in an analog course, I just dropped the link in the chat. Somebody asked for it.
Yeah, someone's asking when will it be? Do you have a date?
Yeah, I don't have a date yet. So I ran a beta course with 6 people from my Zero to ASIC course, and they all taped out in. They took the beta course, did their designs, and did an analog or mixed signal tape out in 5 weeks, and all of them got it on Tiny Tapeout 6. So that's a good start. But now I need to like collect feedback, do the next round of revisions, and then get it ready for sale. So it will be available in the next couple of months. I would have thought 2 or 3 months.
Okay, so I want to pass on one more question because it's kind of a repeating pattern in the Q&A. There's many people who haven't done any tape outs who are really new. They're basically asking, for someone who's really new, what are the right steps to get into this? So let's say you were completely new again, Matt. Where would you start? What would be the thing you'd be looking at, and how
go
would
to
you get into this?
tinytapeout.com.
Yeah.
And then we are actually reorganizing the website at the moment. It's going to be better. We're paying a professional to help us with this. Start off with maybe how do semiconductors work? Do the silly whiz lessons. That will give you the grounding in how semiconductors actually work and what a MOSFET is. Then complete the digital design guide. It's a set of puzzles and configurable designs. And then take part in a tape out. The next one is Tiny Tapeout 7, which is going to be open next week and will be taping out on the 1st of June. So just dive in, get involved. Yeah.
Yeah.
Hit a problem, ask for help, join the community, get started. There's nothing to wait for.
Perfect. I think this is a great way to end this seminar. So on behalf of the community, Matt, thank you very much for spending time with us. This was a super inspirational talk. And I think we hopefully managed to convince people to do exactly what you just said. Get involved and become part of the open source community, and let's drive this forward.
Let's go.
Thank you, everybody. Yes.
Yeah. Thanks everyone for your attention. And thanks again, Boris. Happy to be here.
Thank you, everybody.
Bye.
Bye.